Hello and welcome to the third lesson in the electricity unit. Today we're talking about applying electrical concepts. So our learning goal today, I want you to be able to use your understanding of electrical concepts and related equations to solve some real-world problems. And it's kind of, like I said, it's the start of the electricity unit. We're doing some of the kind of the more of the basic stuff. So it's just warming you up and getting you going. So the first example is how much current flows through a hairdryer if 1200 coulombs of charge pass through in 1.65 minutes. So from the other day or from yesterday, we know that current is a calculation of charge divided by time. All right, so I equals Q over T. Coulombs is a measurement of charge. So 1200 coulombs divided by, now time has to be in seconds because it is coulombs per second. So on the denominator, we need to convert minutes to seconds, all right? And we need to multiply by 60. So when you do that calculation, if you're going to do it all at once in the calculator, make sure you put this in brackets. So the calculator does that multiplication first, and I get 12.1 amps. All right, so that's how much current is being used in the hairdryer. It's a 12 amp hairdryer. All right, so moving down through the note here, electron flow. So the charge, or coulombs, is the number of electrons multiplied by the charge of electron. So if we want to know what the formula is, and it's kind of, mine's garbled in here, hopefully yours printed out a little bit better. Here's the formula to calculate charge. Okay, so Q is your charge. Okay, and it's measured in coulombs. N is the number of electrons. Number of electrons, which will always be a very large number. And E is a constant. It is the charge of an electron. Charge of electron, and that number is there. This is why we reviewed scientific notation at the start. So it is in scientific notation, and it's a very small charge. So each electron carries a very small charge, times 10 to the negative 19. So there is our formula. Like I said, I hope that printed out a little bit nicer for you, but that's what it was supposed to say, spread out. So that's how we calculate charge. So an example of that, how many electrons have passed through a night light. So we're looking at one of those night lights you may have used when you were younger, or maybe still do. And we want to know in one night. All right? So we know the formula is Q equals NE. We know E, it is a constant. We are looking for N, 1.602 times 10 to the negative 19. So we're looking for how many electrons, and we know the charge. So on the other side, to power the night light, it took 2.2 times 10 to the 3 coulomb. We want to isolate for N, so I'm going to divide both sides of the equation by that constant. And when you do the calculation here, we determine that N is equal to 1.37 times 10, and the exponent here is 22. So remember, and that is electrons. So that's the number of electrons it took to power that night light. So keep in mind that 22, that means that after the 137, there would be 20 zeros. So an enormous number when you look at the number of electrons required to power that light. All right. Electric potential or voltage, another formula. We talked about it earlier, and you have this on your sheet. V equals IR. We still haven't used it. That is one equation that will determine your voltage. Here is the other one. And voltage is your energy, the energy required to increase potential, so energy divided by the charge. All right, so it's just another formula out there. So when you do your cheat sheet, make sure you kind of group everything together. So voltage is equal to E over Q, which is equal to I over R. All right, so the example for this one, a static electric charge delivered to you from some nice shag carpet is 1.5 times 10 to the 1 joules. So 15 joules, that's that, you know, that shock when you touch the doorknob. If the potential difference is 500 volts, what was the quantity of charge transferred to you? So voltage, we know V. It's a dead giveaway because of the unit. So 500 volts was given. Now, you need to recognize that 1.5 times 10 to the 1, because it's in joules, that's a measurement of energy. And we are looking for what quantity of charge. Charge is Q. So that's our unknown. So it is using V equals EQ. And the reason I'm kind of doing that process off to the side here is because when you start doing some of the questions, they all get mixed in. So it's kind of important to identify what you know and what you don't know. So 500 equals 1.5 times 10 to the 1 over Q. Remember to solve this. I'll maybe do it in a bunch of steps just to make sure everyone's comfortable when it's in the denominator. Multiply both sides by Q. 500Q equals 1.5 times 10 to the 1. Divide both sides by 500. And we get Q equals a total of 0.3 coulombs. All right, so the actual charge transferred was 0.3 coulombs. All right, and that tells you how many electrons, because remember when we talked about, so this is me kind of rambling for a second, we talked about electrons leaving this particular object and traveling to the other one. Let's see if I can grab it. Nope. So anyway, those electrons, when they move, it is your charge, because charge is number of electrons multiplied by E. So you're calculating this number here is it'll allow you to tell you how many electrons jumped from one object to the other. All right, so really that's what charge is, but instead of worrying about number of electrons, we talk about in terms of coulombs or how much charge. Electrical energy, so this goes along with your energy formulas. So remember, energy was work, force times displacement. We talked about it being mc delta T, so your thermal energy. So this is another form of energy that exists out there. All right, and that's your electrical energy. So there's another formula that needs to get on your cheat sheet. V is your voltage, so we've talked about what that is. I is your current, and again, T is time in seconds. So electrical energy, so how much energy was needed to power something. So my example, I have two examples here. Coffee maker draws 6 amps. So again, I'm going to list my information. Amps is a measurement of current for 300 seconds. That's a time. Using approximately 2 times 10 to the 5th joules. Oops, let's do it this way. Equals 2 times 10 to the 5th joules. Joules is a measurement of energy. What is the potential difference? And I'm going to make a note here. In your heads, you have to know that potential difference is equal to voltage. It's a synonym. All right? You need to just know when you read potential difference, oh, that's voltage. All right? So we are looking for the potential difference. We're looking for voltage. So we only have one formula for electrical energy. E equals the VIT. So substituting in, we're looking for V, multiplied by the current. So current in this case is 6 for 300 seconds. To solve that, we want to get V by itself. We're going to divide both sides by 6 times 300. And when we do that calculation, we get V equals 111.1 volts. All right, so basically it'll be coming from a 120. There's been some loss of, one of the measurements, there's been some loss of energy. So therefore, it uses 111.1 volts, because it should turn out to be 120. All right, so there we go with that. And then down below, we got an electric stove, and electric stoves are connected to 240 sources. All right, not your regular wall socket of 120. It's like a welder. It requires high amounts of voltage. So voltage is 240. It has a resistance. So resistance is R equals 20 ohms. And what is the current? So we're looking for I. So we finally get to use that formula that I talked about a little bit earlier today and before in a previous lesson, we finally get to use V equals IR. So we do the 240 equals, looking for I, and your resistance is 20. So you can see with the basics here with electricity, because remember this is the basics, we get to just do decoding again. It's kind of like the kinematics. I'm setting you up so that next year when you go into a course, you're comfortable. It turns out to be 12 amps. You get into that mode that you can do the basics, you can do the calculations, you've seen that before, so when you get to see practical application in the college or the university level, this stuff's taken care of and you're comfortable with that. Alright, so I'm going to break this up. I'm going to finish this slide and I'll finish in the next video here. What's the total resistance of each circuit? So I have got example A and example B. So example A here, if you look, there's only one pathway. Alright, there's one pathway to follow if I'm an electron. So this is what we call a series circuit. Oops, can't spell anymore. A series circuit. So if it's a series circuit, that means that your total resistance is R1 plus R2 plus as many resistors as there is. So in this case, it's just going to be 10 plus 20 plus 30. So we end up with 60 ohms of resistance. Now this one has multiple paths. I could go that way, I could go that way, I could go that way to get back to the battery. So there's three paths. So we call this a parallel circuit. And for a parallel circuit, it's 1 over the RT equals 1 over R1 plus 1 over R2. So I talked about this before. Now I'm showing you the actual math. So 1 over RT equals 1 over 10, that's the first resistor, plus 1 over 20, plus 1 over 30. So you're going to actually punch these fractions into your calculator. All right? So I'm going to actually punch in 1/10 plus 1/20, and what you get, 1/10 plus 1/20 plus 1/30 equals 0.183 repeated. Don't delete that from your calculator, because what we need to do is we need to flip this fraction to make it RT. So what you do then is take this 0.183, and what you do is you go to the exponent, -1 on your calculator. Okay? Some calculators will have an x to the -1 button that looks like this. Alright, you can just hit that button, but if you leave that on their exact value, so I'm just going to go exponent -1, I get my final answer of 5.45 ohms. Now look at the comparison between the two. This is what is the advantage to having series versus parallel. For a single circuit, and we used the same resistors, it was 60 ohms of resistance. So that's like 60 chairs in your pathway if you think back to our analogy. So the electrons had to hurdle a lot of chairs. Whereas in a parallel circuit with the same resistors, it's 5.45 ohms. What does that mean? So remember, resistance, makes the electrons work. Well, in the cases here, the electrons have to work a lot harder. So if you put 3 lights in a series together, okay, you would need a lot more voltage to keep them as bright as you would over here, because the electrons have to work a lot less. All right, and that's why a lot of our houses, if a light bulb goes in your room, all the lights in the room don't go out. We've hooked it up in series, a lot of segments of your house, because it lowers your resistance and lowers your need for electricity or current. I'll finish this lesson up in the next video. All right, back in a sec.